Uh, all right, cool. Anyhow, I'm going to record this. As I said earlier, hopefully you guys will be able to access it if you want. And I'm going to sort of write on this whiteboard kind of like we're doing class. Hopefully it works. I know it's not the ideal situation, but it is what it is. So feel free to show your face, don't show your face. Feel free to use the chat thing if you want to chat. Or you don't have to chat. You can literally just talk out loud. You guys know how I roll. I don't care. I think there's like a raise hand feature, but I don't know what the hell that is. So if you have a question, start talking. I know some of you aren't shy. You'll do that. A couple things before we get started. I know I posted on Canvas a few things. Most importantly is I have some of your grades uploaded to Canvas, but not all of them. And that's because a few reasons. Mostly because some of your grades or some of your papers are still in my office and I can't access them. So if you are seeing blank things on Canvas where you expect a grade, that's okay. I will update it eventually. Do not worry about your grade. The other thing that you need to look at is notice I put, I changed the grading scale. So as long as you just do all the homework, you're going to get no worse than a C. How's that sound? So that's good. What was the other thing I wanted to say? Oh yeah, homeworks. The best way for you to submit them is to scan and upload them to Canvas. So I'm going to be doing that moving forward. Does anybody have any questions about any of that at all?
Nope. Nah, I think that's just like the summer, right? That PDF app.
Yeah, you know what? It's actually now cell phones, you don't even need a separate app. I know iPhones, you can do it from your Notes app. I was reading that Androids have a similar thing. It's built into your phone now. It takes any pictures and turns it into a PDF for you. So, and that's good because if you're sending pictures via email unless you have free Wi-Fi, that's actually quite expensive. So PDFs are much less. They don't take much space up when you send them. Any other questions about homework or anything like that? Homework, grades, whatever. Feel free to email me until I respond. I am getting, as you would imagine, bombarded by all kinds of issues with this COVID-19 crap. So hopefully you guys stay safe and trust all the nerds and don't touch each other. Okay, let's get started then because, well, we are sort of behind and we want to catch up. So as I said, feel free at any point to yap if you have any questions. So where are we at? So we last met and what were we discussing is we discussed differential equations. Now, I figure since it's happening in the real world, we might as well allude to it with this COVID-19. Let's do it this following way. So before moving to the next topic, let's note current affairs as they are. So, by the way, if you look at this whiteboard, do you guys see like arrows in the bottom right? Are you able to cycle back and forth from board to board? I don't know if you are. Hopefully you can. If you can't, let me know and I'll try to adjust it so that you can jump back whenever you want.
I can't. I don't think
I can either.
Okay, well, we'll figure that out. It might be something that I can switch. I'm also, someone told me there's a way for me to save each one of these as a PDF so that I can post them to Canvas if you want them. I would encourage you to kind of take notes along with me. That would kind of be my advice, but I don't know how you want to do this. I feel like when you write things down, you learn them easier. That's just my opinion, but everybody has their own opinion on that. Okay, so if you're interested, and I guess I have to learn. This is a learning thing for me, trying to write with this, right on this board. It's actually, I'm much better today than I was originally. So if you're interested in the math behind this COVID crap, this COVID-19 and any infectious disease, what you can do is you can Google SIR models. So essentially, we use systems. That means more than one equation. So we use systems of differential equations to try to understand disease. So I don't know if any of you are paying attention to the news at all, but you might have, or any of this, like this idea of what they call R0 and this idea of flattening the curve and all that. Some of that stuff you guys would really be able to understand the math because you've learned some of that. You've learned about exponential functions and things of that nature. So what I want to do is I kind of wanted to pull something up just to show you how kind of this stuff works. So basically, before we move on, I think it's kind of, I don't know, I feel like it's something some of you might find interesting. So if I go and I'm going to share a different page instead of the whiteboard, can you guys see like this web page?
Yes.
All right, cool. So basically, the simplest way we can study how disease spreads, this is a very basic model, is you say, okay, there's three types of people. There's the group of people that can get sick. We call those the susceptible people. So the yellow box means these are the people that could get sick. Then there's another group of people that are already sick. We call that the infectious group. They're sick right now. And then there's the green, that's the people who have already been sick and are recovered. And I don't want to get too deep into this because it's you know, it's not fair to how complicated it is. It's not a Calc 2 problem, but you can at least understand it with knowledge of Calc 2. So if you scroll down the page a little bit and you look at right here, you'll see, can I write? I guess I can't write on here. That's kind of stinks. If you look at these three equations, you see ds dt, di dt, and dr dt. Essentially what we're saying is we're trying to analyze how these groups of people change. Notice that this ds dt, the change in the susceptible, notice that the derivative is negative. And what that's telling us is that there's this population of people, and without any protocol, it's going to decrease. Why is this population going to decrease? Because people are going to get sick. So they're going to go from being not sick to sick. And so if you think about what you know about derivatives and you look at these equations, you can maybe think about why these three differential equations describe how a population might get sick and how they recover. So I thought it was worth pointing out to you that you can Google this stuff and then you can go read about, if you were interested, how the math that you're learning about now is the foundation. It's the language of all the crap that all these nerds are dealing with who are trying to figure out how to stop it. So if you're bored and you want to learn some real world math, there you go. It's not as easy as Calc 2, but you now have the tools to try to learn it if you so desire. Does anybody have any questions about that by any chance? Well, I'm not saying you do, but anybody? Yes? No? Maybe? Yeah. Anyhow, so if you're bored, Google. As I said, you can Google this SIR models, and you can try to use calculus and learn about how disease spreads. Okay, that being said, it's time to move on. So, what is our next topic? Our next topic is what we call improper integrals. So, what does this mean? So, here's how you need to think about this. So, it turns out, we often need to integrate over an unbounded domain. Now, this is kind of, you know, you've heard of the word unbounded, you've heard of the word domain before, but you may have not seen it in this context. So let's maybe think about what that means.
Does that mean we're going to be using limits?
Yeah, that's exactly what it means. But the question is why and how. So let's sort of motivate the following way. So to date, we've only defined an integral on a bounded and closed interval. Remember, how did we start our integration? We started it over an integral, or excuse me, over an interval a comma b. So how did we write that? We wrote it as something like this. So imagine, though, that you have some practical problem. Maybe the function you're interested in is the velocity or the acceleration of a particle. And you'd like to know, okay, we have this particle that's moving. What is its position going to be in 5 years, 10 years, 100 years, 1,000 years? You know, for example, maybe we're studying a comet like Halley's Comet. And we'd like to know what's happening 100 years from now, 2,000 years from now. So to answer these questions, we have a child. Ricky, please go upstairs. Oh my God, we're gonna have kids involved in this in no time. This could be wild. What that would require us to do is the following. So many applications require we integrate over an unbounded interval. So what does that look like? Well, that would look like something like a comma infinity or closed a comma infinity. So what do we mean by unbounded? We'll look at the right-hand side of those intervals. We use the symbol for infinity, which means we don't have a finite end. We keep going and going and going. So why is this an issue? Well, this is an issue Why is it an issue? It's an issue because what is our definition of the integral? Well, if you remember, the definition of the integral required that we took our interval, AB, and broke it into n pieces. Well, how the heck can we take something that's unbounded? It has not a finite size. How can we break that into a finite number of pieces? Well, this is an issue, and let's be more concrete about it. this is an issue because our definition of this thing, what does it use? It uses this delta x equals b minus a over n. And clearly, delta x makes no sense. Makes this. So delta x makes no sense for a comma infinity. I mean, you can't take infinity minus a and divide it by n. That just is, it's a ridiculous statement. So how do we remedy this? We remedy it the way that Daryl, I believe it was you that suggested you take limits. Does anybody have a question right now? I'm trying to build some motivation for this. So what this does is we do the following. So to work around this, we make a new definition. So we can't do our usual definition of the integral because, excuse me, we can't integrate over an unbounded domain using the regular definition because it doesn't even make sense. Not only that, if you tried to apply the fundamental theorem of calculus, it wouldn't make sense. So what we do is we do the following. So if f is defined on some interval a comma infinity, what we do is we define the improper integral. So we're not just calling it an integral, we're calling it an improper integral. And what does this look like? We're going to integrate from a to infinity, but we have to define this in a way that makes sense. So what is the definition? The definition says we're going to integrate from a to b, where b is some number that's arbitrary, and then we're going to let b go to infinity after we take that integral. So this is a concept that is traditionally one that's going to drive you guys in Calc 2 nuts. You will write these wrong. It's not your fault. It's just a hard concept. Everybody that's taken this class, and myself included, does these things incorrectly at first. But it is a very technical and important concept. Does anybody have a question? A comment? Does anybody want to say anything silly? There's 14 of you now. I don't know if we lost one or gained one. I think we lost one.
Did you get frosted tips? Or
No, that's just a light, dude. You would, Daryl, that's a good point, brother. But why in God's name would I get frosted tips if the haircut places are closed?
It's 2020. I don't know, man.
No, and exactly. It's not 1999. Although I did in 1999 bleach my hair. That was cool. Do you guys want a tour here while we're at it? This is fun. If you can see, here's a tour. There's the bookshelf. I'm in my game room right now. Look, you can go, if you spin this way, you'll see the kids' playroom, all their toys. If we go this way, you'll see my other monitor. Look, this is like we're giving you a tour of the O'Grady. This is the game room where all the fun and partying ensues. And then if you can hear upstairs, there's two kids driving my wife. Times are fun. All right. Does anybody have a question, comment, other than my hair, Daryl? That's okay. We got to try to make the best of this insane situation. So what's important to note is if I take this marker, this is a right here, which is good to note, is this is a regular integral. I guess I got to learn how to spell. So let's sort of look at an example to help illustrate how this might work. So let's suppose we want to integrate 1 to infinity of x to the negative 5th power. If we want to integrate this, we need to use the proper definition. And the correct way of doing this is to note this is the limit as b goes to infinity of this integral. Now, the integral on the right is a traditional integral. You guys are all capable of integrating this. What is this integral? Well, it's x to the add 1 becomes negative 4. Divide by that. And you are integrating that from 1 to b. And then now we just have to use a little algebra to rewrite this, or arithmetic, if you will. When you plug in b, what do you get? Well, you're going to get negative 1 over 4b to the 4th power. And then when you plug 1 in, you're going to get something. So we can rewrite this so you plug in b and you get the following. Well, we'll do it slowly, I guess. So we get 1 over negative 4b to the 4th. And then this is minus 1 over negative 4 times 1. So I'm being very, very cautious with my negative signs. And so if I rewrite this, which I'm going to, let me draw a, I guess I can write it underneath. If I reorder my subtraction, this becomes 1/4, because minus a minus is positive, and then it's minus 1 over 4b to the 4th, which if I take the limit results in just 1/4. So you might need to take a moment to think about that. If you have a question, please ask or do whatever. Don't be shy. Any questions?
So that's 4b to the 4th.
Yeah, but what happens is b goes to infinity. So I assume you're referencing this piece down here, right?
Yes.
Yeah, so if you want to drag this problem out more, it's 1/4 minus 0, which is 1/4. So this type of limit, this limit that you see at the bottom of this screen, that limit is the type of limit we studied way back in chapter 2 when you were in calculus 1. And now they're coming back to haunt us. Does anybody have a question? You might notice that there's a pattern here. If you look at this problem, we started with x to the -5th, and then the answer has a 1/4 in it. That is actually not a coincidence. If I change that x to the -26, then you would get 1/25 as your answer. So here's a cool fact. So if p is any number greater than 1, you're always going to get this. The integral from 1 to infinity of 1/x to the power p, this integral is always 1 divided by p minus 1. So you should try to prove this. Because this is a fact that is used throughout this course moving on. So it's actually quite, something that you might want to start picking up on now. Does anybody have any questions about this? Okay, now we need some terminology. So some fancy words. So if the limit exists, such as in the previous example, we say the improper integral converges. So that's some terminology you're going to hear throughout the rest of the semester. The word converges is a very useful word in math. We will be dealing with it for the rest of the term, so yay. Now, first off, you might say, what does that mean? Well, you guys know that limits don't always have to exist. We're going to do an example where it doesn't. So if the limit doesn't exist, we say it diverges. And when I say it, I mean the integral. So there's two new words. You have converges and diverges. Questions, comments? By the way, I'm using 2 monitors and I'm writing on a tab, like this stylus thing. So if it, I'm not trying to be rude. It might look like I'm not looking at you, but I'm not. All right. So let's look at another example. So let's do the integral from 1 to infinity of just 1/x dx. And so what is this equal to? Well, this is the limit as b goes to infinity of the integral from 1 to b of 1/x dx. Now, the integral of 1/x is the natural log. So when we integrate, we end up getting log x evaluated from 1 to b. And when we plug these guys in, you're left with the log of b minus the log of 1. Log of 1 is 0, so you're left with this limit, but this limit is infinite. The natural log is the input goes to infinity is infinite. If you drew a graph of that, you'll remind yourself.
Oh, does this mean we get to have our pal Desmos online with us too?
You can have Desmos, that's right. Yeah, you can at any time. I would encourage you to graph something using Desmos to see that, in fact, the natural log does not have a limit. So what we say is we say the integral diverges. Now, there are all kinds of applications of divergent integrals. A lot of times, since we use the word divergence, we might think that they're impractical, but in fact, they're not. For example, in algorithm analysis, when we're talking about how long do algorithms take to complete, these types of integrals play a role. They're very useful in analyzing that kind of stuff. Okay, does anybody have a question about this example? Or everybody's asleep? I actually think there's a thing on here where I can check it.
Oh, good.
What's that? I'm kidding, bro.
I said.
I'm kidding. You guys know. As long as Daryl's Daryl, will you have better attendance remotely than you did in person? Is this what I'm expecting from you?
Yes.
Oh, this is great, Daryl. This is great. Look, I still have my chemicals. So this is good. It's just like we're almost in class. I have this big thing. Of course, now I have screaming kids upstairs. Okay, so any questions? All right, cool. So we'll give you some practice problems on that. In fact, I think I gave you some on the last homework because we never got to them. So another type of improper integral this occurs when the function is unbounded on this type of interval. So what does that mean? So it means something like the following. So instead of considering the 1 over x on 1 to infinity, consider it on 0 to 1. So what's the graph of this thing look like? Well, that's bad drawing. Let's fix that. Actually, you know what I can do? I almost forgot. We have technology here. Well, let's hear. Can use straight lines, my friends. Look at this. Well, this is practiced. Oh, wow. What a time to be alive. So if you remember, if you go to Desmos or whatever, this guy we have an asymptote at x equals 0. So the function's undefined. Also, what's important to note is that f of 0 equals undefined. So just like in the infinite case, there's a workaround. Here's the workaround. So what this does is this suggests defining the integral from 0 to 1 of 1 over x dx as a limit. The limit is a approaches 0 from the right of the integral from a to 1 of 1 over x dx. Does anybody have a question about this? So we're not going to spend too much time on this, but now I think you can make the generalizations. So let's make a definition. So, oh, not good. So if f of x has an asymptote, of course vertical, at x equals a, we define the integral like this. So let's sort of, I guess I shouldn't, I got to use a different letter here. Let me use, typically we use a Greek letter. We'll use this epsilon. And of course the words converge and diverge still apply. Does anybody have a question? Now, again, I'm going to give you some practice problems to deal with this. We're not going to spend too much time on it, but it is something that you guys will see in some physics classes, and some of you will see in some algorithm analysis classes later on. Look, anytime, you know, another place this kind of stuff shows up too is chemistry. If you have chemical reactions, or if you're in biology, you're worried about how maybe a medicine behaves over time. How will the radiation affect the healthy cells 5 years from now, 20 years from now, 50 years from now, stuff like that. Questions, comments? Uh-oh, I hear ruckus upstairs. All right, so what are we going to do next? Well, for homework, we're going to ask you to make some similar definitions and work out some problems, but I don't want to go through it now, so let's just say it like this. So in a similar manner, we can define an integral like this, an integral like this. So all these cases. I mean, if we're going to positive infinity, we can also imagine going from negative infinity. So we're not going to spend too much time on writing this out in general. When you see some examples, you'll see the obvious sort of changes you make. Does anybody have a question? All right. So does anybody have any homework questions? Anything blooming from a long time ago? I don't know. I feel like it's been forever since we've talked. I guess it has been.
In 2 weeks, right?
I know it's been an eternity, Daryl. What are we supposed to do with ourselves? All right. So then let's set the stage for where we're going to be going next. So here's sort of a theme. So we saw a few weeks ago how we might approximate complicated and or impossible integrals. And how did we do that? We did that using things like Simpson's rule or trapezoid rule or the midpoint rule. You'll remember all that stuff. And that is an important theme. And what we'd like to do is we would like to examine the theme of approximation in a more general setting than just integrals. So let's motivate it this way. So it turns out whoa, not good. So it turns out approximation is a useful tool in many areas. So our next goal is to approximate arbitrary functions by polynomials. So now we're kind of just jumping to a more sort of, we're moving away from integration specifically or derivatives or anything. We are just talking about taking an arbitrary function and approximating it by polynomials. So let's put the word approximate in quotations because that sort of, what does that mean, really? If I say approximate a function, what do I mean by that? We have to explain what that means. And then the next thing we'd ask is why polynomials? Well, as you guys know, what are the easiest things to manipulate? If I gave you an exam with all derivatives of polynomials, you would all get an A. If I gave you an exam where all you were asked to do was to integrate polynomials, you would all get an A. They are very simple. Their graphs are very well understood. And working with them is typically not difficult. So that's why we're going to do it. So let's motivate by considering a problem we would have asked you to do in Calc 1. So in Calc 1, so if f of x equals e to the x, the tangent line is what I'm going to call p sub 1 of x, which was x plus 1. Now, you might not remember that it's that obvious, but if you were to draw a picture, so what's the exponential function look like? You'll remember its graph looks like this. Here's the point 0, 1. And then let's change color. Let's use black, I guess. So I'll use actually a line. That'll be good. So this is the line right here, y equals x plus 1. So in Calc 1, we did this thing called finding tangent lines. And the optimal thing to learn from this is the following. And again, we're being very generic with our terms, but if x is approximately 0, what you have is you have p sub 1 of x is approximately f of x, which means x plus 1 is approximately e to the x. That's sort of the gist of what this means. Now, the way for your intuition to help you is to pick points that are close to 0 and look how close the graph is. Now, of course, the word close is an objective term. It's not precise. And also, when we use these approximation symbols, we're not being precise. Does anybody have a question? All right, so if we go to the next page, here's what was useful to remember. If you go way back to chapter 4, for any f of x, the tangent line is given by, let's just call it P sub 1. I'm not, what is it? Well, if you remember, it was F evaluated at the point times X minus the given point. Excuse me, I put that backwards. Let me write that a little cleaner. So it would be F of A plus F prime of A times X minus A. So this formula that I just wrote was one of the first things we wrote in Calculus 1. This formula comes from the point slope form of a line. So the question arises, why not try to use a quadratic or third degree polynomial instead of a line? So if you come up here to this line that I'm going to highlight with a red border, this line right here, and again, it's not a line. Well, it is, because it's a number plus a number times X minus a number. So, you know, if you sort of, if I put an arrow here and then put an arrow here and then I put an arrow here, these are all just numbers. No, don't, numbskull. So even though that formula looks scary, it's a number plus a number times X minus a number. That's a line. That's Y equals MX plus B. So if we look at the previous page, we say, okay, all right, I have a curve, and then I have this line. And then if you look close to the point 0, 1, you'll say the curve and the line are they're touching, they're close. But over here, there's a big gap. Over here, there's a big gap. And so if we want a quote unquote better approximation, why don't we try to match the shape of the curve? So the last thing I'm going to say is the following, and that is, so it turns out there is a systematic method to do this. And the approximating polynomials are called Taylor polynomials. So does anybody have any questions? Oh, someone wants me to go back to this slide. Does anybody have a question about any of these slides? Don't forget, these slides will all be available on, what's it called? Canvas. Does anybody have a question? Going once. Going twice. Okay. So the systematic way is called Taylor polynomials. What's this doing? Does anybody have a question? All right, so what's next? Well, we don't have enough time to go through it all right now, so what we'll do is the following. Is we will do this the following way. So on your next homework, we will show you how. So if anybody has a question, please ask, whether it's on the chat or voice. Otherwise, I think we'll stop here as far as we don't want to get too far ahead because we want to motivate this properly. So if you have a question, let me know. Otherwise, you're free to leave, and I will upload all this as well as your next assignment, and then we'll move from there. Anybody have any questions? If you don't have questions, feel free to leave because I'm not going to do anything else. And even if I do, I guess it'll be on the recording. Going once, going twice. Down to 13 people still here.
All right. See you Thursday.
Bye, Daryl. I'll see you guys Thursday. Stay out of trouble. All right.
I will ask one question, though.
I'm listening. What's up?
So I was like spending time just looking stuff up over the break.
Yeah.
And I want to ask, like, how many possible ways are there to do like the Euler integral?
The Euler what's the one? The series thing?
E to the negative
Yeah.
x. Because I've seen another way.
Wait.
Like,
I'm not exactly sure which one you're talking about. Are you talking about? Hold on. Let me get a. Can you still see this board? I don't want to erase this. Can I get another board? Well, give me a second. Let me. Let me make sure I'm sharing the correct thing. Can you see a blank board now? What do you see?
I'm seeing you creating a new blank board.
Okay, that's fine. Ah!
Now I can't see the blank
Yeah, that's
board.
okay. That's all right. That's not your fault. That's I have to bring it back up. All right. So let's see. What do you see now?
Now I see a blank board.
All right. So are you talking about this sum?
I'm referring to. I'll just send you a.
Or can you send me something?
Yeah, I have a video link which does it in the integral which I'm referring to.
How are you
Gaussian.
sending it? Are you emailing it or what?
No, just chat.
Chatting it? Yeah, let me see.
It was the Gaussian integral.
Gal, so the integral e to the negative x squared?
Yeah,
How come it's not showing me your chat? What the heck?
I sent it directly to you. Maybe it's
I understand that, but I'm not seeing anything.
to everyone.
When I go to the menu for chat, it's not there. I don't know why. Here we go. I got it. So this is a YouTube link.
Yeah.
Let's see.
Actually, I think
I
that.
got an ad. Hold on.
Strange times.
Yeah, that integral.
Okay, so this one, how many different ways? There's lots of different ways.
Yeah,
I
because
could probably think of,
I got 2.
there's probably more than that, but they're almost all high-level methods. The most basic method is what we did in Calc 3.
The not
Yeah,
polarization.
well,
but the-
yeah, you have to write it. You have to take 2 of these. You use Fubini's theorem. And then there's a couple other things. Now, you can also do this by using this trick that Feynman did, which is you integrate and differentiate. You swap the integral and the derivative. So I think that's what this person's doing.
Yeah, that is exactly what this.
Yeah.
Good morning, Flemmers. Fellow mathematicians.
Yeah, so that's a famous one of doing it.
Doing the Gaussian integral today.
So that's the standard way of doing this trick you have. But the reason people don't do that in class is because those theorems about interchanging the integral and the derivative are highly technical. They're not clearly true, even though they work here. So mathematicians sort of have this this mantra that unless you can rigorously show something, you shouldn't teach it in class. So that's sort of why that method. Most people would say that's probably the easier method for actually doing it. Do you know what I mean?
Yeah.
But